you for coming for part 3 of lecture number 24 by Dr. Emanuel. This is on divergence and curl. We have been covering the divergence. Now we're moving into curl. The definition for curl is that we have a curl at a point in our specific function describes the local angular velocity of the vector field around that point. Before, we've been finding change of velocities. That's what we've been finding, the maximum velocity when we did our gradient. So here with our curls, we're finding our angular velocity around a specific point. And as you can see, you'll be cross product. Okay, that's what you'll be using. So the gradient gives us a vector field when it starts off with a scalar. Okay, so when we finish with a gradient, we have a vector, but we start off with a function that's just a scalar field. When we use divergence, it gives a scalar field from a vector field. Start off with a vector field. Now, when we start doing this, you'll be able to see that we can do vectors and we can feed one into the other. So if we do a divergence and we wind up with a scalar, then we can use this divergence back into our gradient to come back with a vector. Notice that. Then we have our curl. It gives us a vector field from a vector field, so it keeps it a vector field. Doesn't change it. Where the gradient changes it from a scalar field to a vector field, where the divergence uses a vector field and changes it to a scalar field. Okay, let's look at this specific example. We have here x, y, z all in one axis, one direction. Okay, just our j component. So that means we no longer have a component for the f of x. We don't have a component for the f of z. So the only component we want to look at is f of y. Okay, so if we look here, when we do our cross products, we know if we're trying to find for the I, we cover up the I, and then we just have our j and k. So our partial of our f function with the component of z, and taking a partial as it relates to the y, minus the partial of f with the f component, the y component of the f, in relationship with the partial of z. That gives us our I component. Minus our, we cross off the j, blot out the j, and we have our partial of f, our function as if in the z component, but we're taking it in respect to the partial as it relates to the x component with respect to x. Then we are taking the minus the partial of the function, the x component, and we're taking the partial as it relates to z. That gives us our j component. Plus our, we wipe out the k column. When we wipe out the k column, what we have left is the partial of the function as of the y component of the function. We're taking the partial that relates to the x component. Then minus the partial of the f component of the function. and we're taking the partial in respect to the y component. That'll give us our k dimension. So, if we look here, we will see that we only have f of y. That's the only component that we have. So if we look here at f of y, we can take f of y as relates to what? Z. Okay. F of y as relates to z. And that'll give us xy. So that's a minus. We can look again. We have no fy's here for j. We have one fy here. And we take the component fy, and we're going to take the partial with respect to x. Take respect to x, and you're just left with yz, positive yz, in the k direction. Okay, so if we put all this together, what we get is our curl of this specific function, we get a minus xy in the I component, and then we have yz in the k. Now we said that curl relates to angular velocity. Example, we're using a velocity of a particle on a rigid body. Now, it is very tricky as you use the angular momentum, the angular velocity. You're going to have two cross products, and when you have two cross products, you can use this identity. Then you have to be very tricky with this identity. So there's lots of issues that you have to look up to solve these problems if you have the angular velocity components. As you can see here, we want to find the velocity of a particle on a rigid body. So you see it's going to do an omega, it's going to do an angular velocity. We need to know the length of this r and this change, and that's what the velocity is equal to. So if we want to take the del of the velocity, okay, or the curl of the velocity, but you already have what? The curl, not a curl, just a cross product of the angular velocity with r. So then you have these two cross products, and you can, by definition, you have to look up a theorem, and you can use this formula. That's what we're using here. And when you convert it over, this turns into 3 omega, and this turns into minus omega, and you get a 2 omega. And you have to look this up. This is a very difficult problem. But I wanted to just introduce it to you so that you can see. Didn't want you not to be able to see what we have. Okay, so now we have the curl vector field provides the rotation of velocity of a vector field. Notice we're using what? The absolute value. Remember, this is a vector field, and now we're converting this part. When we take the magnitude of it, we're converting it to a scalar. Rotating the velocity, rotation of the velocity of the vector field. Then we have the rotational axis of the vector field. And that's what we were looking at, the rotational axis. That's what we had talked about, how it changed. And this is a curl, not the magnitude, the actual curl. Now, whether the field is conservative or not, when we set it equal to 0, we will see it'll become a useful integration. form a line integral. And we'll run across this a lot. Because remember, you have some that'll be changing angularly. We showed you that. And we're going to be going back and reusing those same examples. Okay, remember this is the curl. Okay, so I have this specific function. And so I want to take the curl of that. So this is for my x, my y, and for my z. We have over here f of x, f of y, f of z. There is no z component. So, as we go about to perform this, we'll see here that we explained before of how we actually break this down and get each of the components. And so, as you can look here, we will see again that this is only the x and the y, and we see that all of these are going to 0. Okay? So you need the y with respect to y, which you're not taking. You're taking everything else with respect to y. And the same thing with the x. You're taking everything except with respect to x. It gives you 0. So it says it's not circulation. No circulation. Okay? Okay, at this time we're going to take a break because we're 12 minutes in. We don't want to drag this on. And so when we come back, we'll be going over an example. Thank you.